Now listen up, Lung Gang. I've always got your back. On to the more important stuff. We need to be focused on paper 3. I'm a man of my word, so like I said in my paper 2 stream, then I'll go through a couple of applied questions with you the night before your exam, live on stream, just like I did with Pure. Nice. But you guys have shown mad love. It's been crazy. So here's a new challenge for you. If you get this YouTube channel to 10K before the 19th, then I'll do a Lung Gang special of a 12-hour long stream covering a mad, enormous amount of papers so that we cover every single question needed to pattern your A star. So blow this up, share this with your friends. Lung Gang on top for real.
Hey YouTube, in this video I'm going to cover forces and Newton's 3 laws of motion. I hope you enjoy the video. There's 3 laws you need to be aware of. Newton's laws of motion. The first one, law 1, is that every object continues in a state of rest or uniform motion in a straight line unless acted on by a resultant external force. Now, you might be wondering why I've got this weird person, this dummy figure in this car, right? Now, think of it like this. If you are sitting in a car and you're in a car with no windshield and no seatbelt, and say you're driving this car and you crashed into another car, say there's another car here. Say you crashed into this car, because you're not wearing a seatbelt, you're going to go flying that way, right? Let's say the 2 cars crashed and you were traveling at 30 miles per hour. Now this is a big if there was no gravity and there was no air resistance, what would end up happening is you would end up traveling in a straight line forever. You would actually just keep flying, you'd basically be hovering off the ground, yeah? You wouldn't change because there's no external forces acting on you. It's only because of the external force of gravity that it brings you down to the floor. And there is also things like air resistance, which push back on you, which slows you down. Yeah. If these forces didn't exist, you just keep going in a horizontal line forever. Yeah. In fact, you'll go circling around the earth. Yeah. That's what would happen. So every object continues in a state of rest or uniform motion in a straight line unless acted on by a resultant external force. The best way you guys could see this, if you go on an ice rink, yeah, this is you. Let's say you're happy, on the ice rink. If someone pushes you, you notice that you just keep moving, yeah? In fact, you'd go to the other side at nearly the same speed. Because ice has barely any friction, you keep moving at the same speed. But because it does have a tiny bit of friction, you will slow down slightly. But if there was completely zero friction, you just keep moving. Yeah. Law 2, the resultant force acting on an object is equal to its mass multiplied by its acceleration. Now, you should have all seen this, F equals ma, from your GCSEs. And maybe if you've seen it before. But you can, through experimentation, you can kind of understand why this makes sense. So say you took a pebble. Yeah, say it was like 3 kg and you wanted to throw it. Yeah, you wanted to think about that shot putter. Yeah, you want to take a 3 kg, 3 kg might be a bit too heavy, but say you're super strong. Yeah, you're going to try and throw that 3 kg ball as far as possible. Let's say you want to accelerate it at, 3 meters per second squared. You'd require some strong force to do that. Now, what if you increased the size of the object, 5 kg, and say you wanted to throw it at the same acceleration of 3 meters per second squared? You got to think, okay, would I have to throw it with more or less force? Well, the answer is more. Yeah, so what you're basically saying is if you increase the mass, the force also has to increase. Yeah. Similarly, say you kept the mass the same and you wanted to throw it with a faster acceleration. If you wanted to throw it with a faster acceleration, then again, you would need more force to do that. So also, if you increase the acceleration, then the force also has to go up. So they're kind of in proportion to each other. So technically, you lot have all done proportion from your GCSEs. The force is also always proportional to the acceleration of an object. So experimentally, yeah, it makes sense. F equals ma. The more mass there is, the more force you have to exert. If you want to make something accelerate faster, again, you have to increase the force. Yeah. So that's Newton's second law, F equals ma. The last one is when an object exerts a force on another, there must be an equal and opposite reaction force. Now, a simple, there's a few things you can do for this. One, I'm going to tell you, but I don't recommend you do it. But you could, I've got my little coffee mug here. If you take that and you put on the table, say this is the table, you can see that the coffee mug, you can see the coffee mug is not going anywhere because my hand is exerting a force upwards, which is equal to the force pointing downwards. Otherwise, it would go through my hand. Yeah. Another one, this is the one I don't recommend you do. Go up to a wall and punch it. And then you'll feel the resultant force of you punching the wall. Yeah. Unless you're super strong and you break the wall, then that's a bit different. But just say the wall stays intact. You punch the wall, you'll feel that resultant force. That's Newton's third law. Yeah. Another cool one is, I'll never forget this from my physics teacher. He actually did this experiment with us. So if you get a bucket of water and you fill up the bucket of water and you spin it around, this one you can do at home. It's hot outside, so spin that bucket around. You'll find that the water does not come out because of call this a centripetal force. Yeah, it stops the water from falling out. So this is Newton's third law. So now, force diagrams and common forces. Whenever an object rests on a table, what we were talking about before is the resting force, the normal reaction force. That was like, do you remember when I took my mug and I put it on my hand? There's always a force pointing upwards. My hand is pointing a force upwards to stop the mug from falling through my hand. We call that a normal reaction force. The mug has a weight, right? It's pushing down into my hand. That's the downward force that you see. Yeah. Now, when we get into like more into depth mechanics, we're going to be talking about particles. For all particles have weight unless they are defined as being light. This always acts vertically downwards. Now, when we get into more in-depth forces, we're going to have an object and we're going to have something that's trying to drive it forward, to move it. There's always going to be a resistive force to try and stop it from moving. So over there is like the four most common forces in force diagrams. Yeah. So an upward force, a reaction force, downward force, the weight, something that's trying to drive it forward, something that's trying to resist its motion, which commonly is friction, right? We like to discuss friction all the time. Yeah. Cool. Some extra forces that we like to use, mostly in quite difficult year 13 questions, but we have tension. Tension is a force that prevents two objects moving away from each other. It is often found in strings and rods. So, you could just take a pen. If you pull that pen apart, it doesn't break. Yeah, that's because of tension. Tension is the arrows would be pointing back towards the center of the pen. Yeah, so the reason you can't pull the pen apart is because of tension. Yeah. Another one is thrust. Thrust is a force which prevents two objects coming together. It can be found in a rod, but not a string or a rope. I do actually have a string here. If you guys, I don't think you can see it because like a thrust means pushing my hands together, but you can see that the string, I can push the string together. Thrust can't act in a string. But with a pen, look, I can push the pen together and my fingers do not come together, right? That's because there is a thrust force that is pointing out this way, outwards. So I can't push my fingers together because the thrust force is stopping me doing that. So rods, like a pen, is super powerful because you can pull apart and it will stop you doing that. You can push together and it will stop you doing that. So it can be found in a rod. The legs of a chair provide a thrust force that prevents the seat of the chair falling to the floor. Yeah. Unless you're like me, I'm 100 kilos. When I was in school, I remember going to one of the year 7 classrooms and they always have really tiny chairs. And the swivelly chairs, they're like made of plastic because, schools like to invest in really cheap chairs. And I remember sitting on the chair and I snapped it in half. Luckily, there was no kids in there, but it was pretty funny nonetheless. I just blamed someone else. It wasn't my fault. Anyway, equilibrium of forces. So an object in a state of rest or moving with constant velocity is said to be in equilibrium. This is law 1. Yeah. So let's look at a very basic example. What can you say about this particle? So we have a particle, we have a force pointing upwards of 5 newtons, we have a force pointing down of 5 newtons, a force pointing to the right of 30 newtons, and a force pointing to the left of 15 newtons. Well, you can see that the upward force and the downward force are balanced, right? They're equally up and down, but you can see that the right force is bigger than the left force. I don't know why I did that. That's supposed to be a bigger than, yeah? So this force here, 30, is bigger than 15. Which must mean then that if we were to, leave the particle alone and just those forces were acting on it, it would be acting to the right. Yeah, it would be moving to the right. But obviously we want to write this algebraically, and this is where vectors come into play here. Now you remember from GCSE, column vectors. The top number represents movement in the x-axis, the bottom number represents movement in the y-axis. So this is left, right, and this is up, down. Now we can rewrite all of these as vectors. If I call this up, the up vector 5 is going upwards in the y-axis. So as a vector, we're going 5 in the y-axis and nothing in the x-axis. Yeah? This force down here is in the y-axis, but can you see it's going downwards? We remember from GCSE translations that if we're going down, then we need to write negatives. It's going down by 5, so we'd write -5. But no movement in the x-axis because it's strictly pointing vertically, right? This 30 newtons, you see it's pointing to the right. That's in the positive x-axis. So it'll be 30 in the x and nothing on the y because there is no y movement. And finally, 15 is pointing left. So it'll be -15 and 0. Now the beauty of vectors is that once all forces are in vector form, to get the net vector is we just add all of them together. Add them all up. Now if you read the top row, you can see 0 plus 0 is 0, plus 30 is 30, subtract 15 is 15. And when you add the bottom line, 5 minus 5 is 0, plus 0 is 0, nothing. So when you read this, can you see we knew this already, 0. There's no movement up or down. Yeah, no movement up or down. But here, can you see we said before that we would be moving right because the 15 newtons is the net force pointing to the right because 30 is 15 bigger than the force pointing to the left. So this is what we do in A-level maths. We write all the forces in vector form and then we just add them together. We call this the resultant force. Resultant force. Or the net force. But the best way to say is the resultant force. So what we're going to do, we're going to practice this today, is we're going to write all our forces as column vectors, add them up, and then that will give us the resultant force. Then we're just going to do some small algebra with it as well. So hopefully that makes sense. If it makes sense to you for now, put some plus in the chat. And I can answer Simran's question now. Simran, how did you know you wanted to do a maths degree? The simple answer is when I was at A levels, I decided I wanted to do what I felt I was best at. Yeah. So I always recommend carry on doing what gives you the most energy and what you are best at, because usually what you're best at is what gives you the most energy. And if you're going to do something for the rest of your life, if it's going to define your career, do always what gives you the most energy, and that is it. Always go with energy. I'm big on the spirituality stuff, yeah? So energy is always most important. Maths gave me energy, and it still gives me energy to this day. So that's my best piece of advice when deciding what you want to do at uni, yeah? Now, there's going to be some notation here, which I'm going to have to explain what it means, but don't worry, it's super easy. Alberto, so this is the beginning of forces, but it does get trickier, but not yet. But see how you go. Obviously, I'm going to build it up. But obviously, the whole point is that we want to make it seem easy, so all the hard stuff also seems easy. But it's important that we build it up slowly and it makes sense in your head first before we can go to the hard stuff. Yeah. So 3 forces, F1, F2, and F3 act on a particle P. F1 equals 2I minus 3AJ. So now you might be thinking, what does I and J mean? Now I just essentially means x-axis, and j means y-axis. So this f1, I'm just writing on the side for now. And if I underline my letters, it means I'm talking about a vector. Yeah. So 2i means that it's 2 on the x-axis, minus 3aj means minus 3a on the y-axis. Now, as an examiner, I always want you guys to write as column vectors, because reading column is so much nicer than I and j. I and j is very common with physicists. Even though they do like to do columns, it is very common with them. But also the reason I's and J's are used a lot is because as examiners, when we're typing questions, it's easier to just type I and J than it is to format the column and write stuff in like that. So, you know, whenever I see I and J, wherever we see I and J, we're just going to put it into columns. Yeah. So if we were to rewrite all of them, I haven't even read the full question yet, but let's rewrite all of them. So F1 is 2 minus 3a. F2, so you can see it says 2ai, so it's 2a on the x-axis and minus b on the y. And finally F3 is bi, so just b and minus 4j. Yeah? The particle P is in equilibrium under the action of all of these forces. Find the value of A and the value of B. Now, equilibrium means the resultant force is 0. So if we were to go back to this, if the up, down were the same and the left and the right were the same, all of those vectors would have added to 0, 0. Because if that 15 said 30, then this up here would have been minus 30, and then these two would have added to 0. So anything in equilibrium as a vector must add to 0. So nice and simple. Equilibrium means we're going to find the resultant vector by adding all of these up. And then we just equate it to 0, 0. This must equal 0, 0. If it's in equilibrium, they must all balance out. Now, if you read the top, it says 2 plus 2a plus b equals 0. 2 plus 2a plus b equals 0. Move the 2 over, we get 2a plus b equals 0. Reading the bottom line, we have minus 3a minus b minus 4 equals 0. I'd probably prefer to move the minus 3a and the b to the other side. So we have 3a plus b is minus 4. Yeah, so I've just taken this bit to the other side and I've kept the minus 4 here. Then we could just take away the two equations to cancel out b. Taking them away. I might go backwards this way. So I'm reading bottom up. 3a, take away 2a is just a. b, take away b, they cancel. Minus 4, take away 0 is just minus 4. So there's your a. And then we just sub it back into any of them, and then we'll get our b. So subbing into the first one maybe. So we have 2 times a, which is minus 4, plus b equals 0. 2 times minus 4 is minus 8, plus b is 0. So there you go, b is 8, nice and easy. So remember, in equilibrium, all forces must add to 0, 0. And in year 13, you do 3D, so there'll be I, J, and K. Oh yeah, equals minus 2, sorry you lot. Wasn't concentrating there. Sorry, that is 0, but when you move the 2 over, it's minus 2. Good spot, good spot. So we're doing minus 4, take away minus 2, which becomes minus 4 plus 2, which is minus 2. And then 2 times minus 2 plus b is 0. 2 times minus 2 is minus 4. Move that over, b is 4. All right, next one. A particle begins at rest at the origin. It is acted on by 3 forces, 2i plus j, 3i minus 2j, and minus i plus 4j. And remember, the n means newtons. That's how we measure forces. Find the resultant force. So remember, resultant force means we add all of the forces together. We want to keep them in column form. 2i plus j. 2i means 2 on the x. J on its own means the coefficient is 1. Plus 3i minus 2j. So 3 minus 2. You're basically just reading the coefficients. Minus 1, 4. Reading the top. 2 plus 3 is 5. Minus 1 is 4. 1 plus minus 2 is just 1 minus 2, which is minus 1. Plus 4 is 3. And you can put newtons there if you want. Now, to be very clear, you do not have to write this back in INJ. You could just say 4i plus 3j if you want, or you can leave it in column form. Any of those is fine. As an examiner, I prefer you to write column because it's easier for me to see. Yeah. Work out the magnitude and bearing of the resultant force. Magnitude and bearing. Now, remember what this means from GCSE. 4 means you're going 4 to the right and 3 up, right? So if you have a particle here, you're going 1, 2, 3, 4 across, 4 to the right. You're going 1, 2, 3 upwards. So the particle, which is being acted on by this force, is going in that direction. Yeah, if the resultant force is 3, 4, it means if you took a particle, it would be traveling in that direction. Yeah. It wants to know the magnitude. Magnitude means size. What is the size of that force? What is the size of this triangle with sides 4 and 3? Well, we know that means Pythagoras. It's asking for what is this length? What is the size? Magnitude means size. So x in this case would be the square root of 3 squared plus 4 squared, which hopefully we know is 5. And we could say newtons there. Magnitude. And then bearing. We know bearing means relative to north. So if the particle is here, it's saying relative to north, what direction is it traveling in? So we have to draw a north line. And it's asking for this angle here, theta. We know that's what bearing means. It means from north, how much do you need to rotate to get to the direction of the trajectory? Now, hopefully you guys remember from your alternate angles rule from GCSE, or the Z rule, but you'd never call it the Z rule, is you remember that that angle theta is the exact same as this angle theta over here in this right angled triangle. So tan of theta is the opposite 4 divided by the adjacent 3. Then all we do is we do inverse tan. And on our calculators, in fact, my calculator is still on the binomial setting from our session before. Inverse tan of 4/3 is about 53 degrees. But remember, if it says bearings, we need to have 3 figures. So it'll be 053. You will lose a mark if you don't put that there. Right guys, I hope you learned something new today and you enjoyed the video. If you did, feel free again to subscribe and like the video. Share it with your friends if you feel like it will benefit them as well. All the details are in the description below, and I look forward to seeing you in my next video. Peace.